Okay, then we're going to start. Good morning, everybody. Thank you very much to attending this DOS Award 2023. My name is Frank Maatje. I'm from Bouwen and Staal in the Netherlands. Next to mine are colleagues from Delft University, Jerica, the left side, and Milan, the right side. We three will do the presentation today of this third DOS Award, an international award for master theses of students who are active in the field of steel constructions. This year we have a special version because besides the normal prize for the winner from 2,500 euros and for the second best 1,250 euros, there is also an interesting prize. And this prize is made available by Zeeman. And the prize is that the winner will also be give the opportunity to present his master thesis or her. Sorry, same problem. Her master thesis at the Eurosteel conference, which will be held in September in Amsterdam. So an interesting audience of more than 500 people who are active in the steel industry around the world. First of all, I want to thank all our sponsors, the sponsors who made this award, this international award, again available. The ECCS, the European Convention for Constructional Steelworks, the SNS. It's a Dutch Association of Steel Fabricators, the Severfield, an international steel fabricator, Boardman, a deliverer of machines which are used in the steel industry, and by Zeeman, also an international steel fabricator. I will give now the word to Milan, and Milan will talk more about what the DOS Award is.
Yes. Thank you, Frank. This year we have received more than 25 submissions. From those 25 submissions, international jury consisting of 17 members have selected 6 nominees for today's presentation. Some of these jury members will join us during the presentation because we have 10 minutes for each student, each master thesis. And then we have 5 minutes of the questions. The rule of our game is that these questions will be asked by the jury members. And of course, if we have time enough, then attendees will be also able to ask a couple of questions. All has to be within 5 minutes. And today we have Angeliki who will take care about timing and interrupt everybody, including me.
Exactly.
But before we go on, I want to thank to my colleagues who supervise and organize these master thesis projects, and then of course all master thesis students who made a lot of efforts first to write that thesis and then present it at the domestic university, and put some extra efforts to give us today 6 presentations, which I think it would be outstanding. They have done an excellent job, all of them, and I hope we will have a nice day full of the newest development, both in the industry through our keynote speakers and the research, but also at the level of master thesis students.
Exactly. Thank you, Milan, so much. So we have a wonderful lineup of presentations from our nominees, but also from some keynote speakers. I will give a warm welcome to Peter Zeeman, who is our first presenter. Until he makes some time to share his screen, I'm going to go a bit in the logistics. So we have 2 voting sessions, one from the jury and one from the public audience. The jury is the one, fortunately or unfortunately, that will decide the winners. And the audience is just there. I'm going to give further instructions, of course, to how you can vote, and you can show your preference by selecting the one that was your favorite. And then, yeah, Peter, you are welcome to share your screen and kick off this awards ceremony. The virtual stage is all yours. Please share your screen
Okay, thank you very much for the introduction, Angeliki. Honestly, I didn't intend to share a screen, so I'm just talking to you. Yeah,
Okay.
that's how I'm, in my age, we are used to do it like that. And I'm not so good with a picture presentation. So what I want to introduce to you is some thoughts about the building industry as the most unclean sector of all, yeah, and how we could proceed. And I want to share some ideas how we can go on without falling bad in desperation. So, as we all know, there are huge discussions about the Green Deal, and meanwhile, most of us accept the necessity of a greener behavior. Nobody seems to know what we can do and how we can achieve the target. It seems the industry is waiting for governmental and legal decisions. Yeah, so there's some activity, but I'd say not too much. Yeah, and also in most groups, I hear we are waiting for this from Brussels and we're waiting for that. But I think we should do it ourselves, yeah, if we are convinced to do the right things. Yeah. Well, that makes that seems we want to get a solution from politicians and lawyers instead of technicians. Yeah, and I think we don't really want this. That will not work how we are doing that. We need technical solutions. We need new technologies, an evolution, maybe not a legal revolution. The society has to act as a whole, to be convinced as a whole to work on a Green Deal, as that has worked in the past. For example, when Henry Ford started Industry 2.0, he didn't even know that this exists or what that means. He just did what was necessary, and he didn't wait for politicians what to do. And many of us know the building sector needs about 40% of all resources mankind takes out from our planet. It can be 38 or 42, whatever, a lot, and more than any other industry. And that makes it the most resource demanding business ever. It sounds harsh, yeah, but it's just a fact we should face. There's a huge backlog in poor countries. When you compare, according to Werner Sobeck, people in the rich Western countries own or have about 480 tons of building materials each person, including the babies. That, of course, includes a share of roads, hospitals, schools, or administration buildings. In comparison to that, people in poor countries have about 5 tons available per person. And we know there are more poor than rich countries on this planet. That means people in highly developed countries take about 100 times more resources for buildings than people in poor countries. And I think in our own interest, we better adapt and expect that those people, those poor people, want to improve their situation in future. Otherwise, we will face huge social problems and we will have more war than we have now already. The ecological footprint of building materials should not be the central issue in my speech, because this is mainly the business of the steel mills and other material producers. But as construction companies, however, we should ourselves find ways in our own service fields to save resources of whatever kind in construction. And we can do a lot. Engineers and construction people have a huge influence on how much resources are used in our sector. And we have to contribute to a solution, and we have a lot of influence in doing things much better than now. We are working with steel, and that means we are very well prepared to contribute to a better and greener world, because steel and structures made of steel have excellent characteristics. A few of them are: steel structures have a recycling rate of more than 99%, and this since decades. This isn't something new. This isn't greenwashing, because when we started with this, there was no greenwashing this time. And the recycling rate is much more than in glass, or even more than gold. Yeah, everybody should know this and keep that in your mind. Steel allows easy adaptation of structures to new uses, meaning we can enable convertibility. And steel allows easy repair and maintenance. Steel structures are light and compact. Many elements can be loaded on a single truck or a single train coach. Steel is highly predictable, very consistent, that allows a very safe design. I don't want to be too scientific here. I just want to show some samples or references of my own company, where to start and what to do, even if there is no regulation yet. Please don't assume those measures will save the world or that we are the ones with the only or best solution. I just want to inspire you to move forward and not to wait. A few instances of intra-sector, inter-company activities might be the engineering, for example, that defines how much resources are used in the building. That is very much depending on the design. The transportation is an important factor. There are airplanes, there are trucks, trains, and ships. Yes, we already delivered via airplane, but it was not in my will. I know that our project managers hate transportation because this is not reliable, because the train companies in different countries are not cooperating very well. Yeah, but still, trains can reduce the environmental footprint of our business a lot. There's also the consulting. Our clients have a lot of trust in us because they give us orders for millions of euros. So that means that there is some feedback. Okay. That means they trust us a lot. Yeah. So we can convince them to at least to prepare for photovoltaic. Yeah. We also can talk to them if it's really needed to tear down a building, to demolish it, or can we help to restore it? We can offer solutions that clients never thought of before, and we are doing that, and we did that a lot in the last decades. Yeah, there's also how we think about investments. Is it only the monetary factor that counts, or do we think more into the future and deeper into the future? For example, last autumn in October, we installed a filter ventilation system in our factory in Poland. That is a smaller steel construction factory with 10,000 square meters, and we reuse the heat that is in the air in the building coming from cutting or welding. And that meant, and I was surprised, I have to say, we didn't have to turn up the heating system at all last winter, even though that outside temperatures of -10, even -15 degrees. Yeah, so the things work. I'm not sure if we get a return on investment on that, honestly, because it was a very expensive decision, but I'm happy it works, and energy will jump up and down with the prices, but in general, it will go up for the next years and maybe then down again. So maybe there's a chance to get the return on this investment, but I'm still happy we did it. And don't underestimate, we have an influence in our stuff, and we can do some cultural development. With simple instructions, we can influence the people in our companies and institutions. We can instruct them how to handle waste paper, ensure less paper consumptions with IT solution, prohibit with just a simple email, prohibit plastic bottles, coffee capsule, water drinking bottles, all those little tiny things. Of course, that will not help a lot, but maybe it will help because people will integrate those behaviors in their lives as soon as they see it's not damage for their life, yeah, and it works, yeah, it doesn't do any bad, yeah, and they also will show this behavior to their families and maybe friends and the society. We can help a little bit to change the society in their thinking, and I think it's worth it. All of this is important, and we can save 1% or 3 or 5 or sometimes even 20 or 30%, but still that will not be sufficient to save the big share of resources needed in our sector. And the big question is, can we also save 50%, for example, maybe even more sometimes at once? And I say, why not? There is a very simple answer. We just have to use our buildings double as long, and we will save about 50%. We are working since many years how to reach this goal. Yeah, and I want to start with with a special project, not of our company, of course, yeah, but a building that survived a long time, a building that was also used in very different ways. And I'm talking about the IG Farben building in Frankfurt am Main. IG Farben, it's some kind of a old factory of the 30s of last century. So we know there was a dark time in Germany, but still this industrial building was built in 1929 as an administration building. The architect was Hans Pölzig. And during the early Cold War, it was transferred to the United States Army Europe as their headquarter building. And since 2001, it is part of the Goethe University. And I say that those are quite different utilizations for one building with the resources that were originally used in 90 years ago. Yeah, of course, the structure is made of steel. I just want to say this. Yeah. And I have to ask, how many buildings have been demolished and replaced in the last 90 years? So how can we achieve a longer life cycle? It starts with the design. Of course, we try to reduce material quantities with the design, optimize transport routes and so on, and loading to save money and to make the ecological footprint better. But we also can enable convertibility from the start. Yeah, if we think.
Thank you so much. Can you hear me?
Yes.
Nice. We only have allocated 10 minutes for this presentation, and I think it's time to.
Oh, I thought it was 15 minutes. Yeah, I didn't know that. Yeah. So, okay.
We can let you in a little bit later if we have more time, but we have to give the word to our first presenter from Sweden.
That's fine. Yeah, that's fine.
Okay. You asked me to be very strict about it, so that's why you had me interrupting you. I'm so sorry for that. Maybe we can try to find another spot to analyze your thoughts. Thank you so much, Peter. And so I think now it's time to introduce our first nominee. It is from Chalmers University of Technology. We have Ala Akur and Ziad Mili. So please, guys, share your screen. Exactly. That is great.
So, thank you, Peter, for your presentation. So, hello, everyone, and greetings from Gothenburg, Sweden. My name is Ala Ashur, and
I'm Ziad Mili.
So, we want to welcome you to the presentation of our thesis project regarding the flange backplane behavior of stainless steel girders with trapezoidally corrugated webs. Okay. So the primary aim of the investigation has been to determine a suitable design model for the design of trapezoidally corrugated web girders in stainless steel. So we focused on the proposal of a model approximating the buckling coefficient and the reduction factor related to flange buckling. Now, in the next few slides, let us introduce a brief background related to our thesis subject. So the idea behind using a corrugated web plate is to increase a shear buckling capacity. So meaning that thinner web plates can be used without the need of vertical stiffeners. This contributes to reduce material use and production costs. The shape of corrugation can vary. For example, it can be sinusoidal or trapezoidal, and the trapezoidal corrugation is the most common one and created in this thesis. So continuing to the material aspect, why should stainless steel be preferred against carbon steel? Some major reasons include an improved corrosion resistance, higher strength to weight ratio, and a better performance in extreme heat. So for the design aspect of corrugated web girders, more specifically the flange buckling resistance, there are various design models available for carbon steel, but the issue is that there is no commonly accepted procedure. For instance, there are several suggestions on the buckling coefficient used to calculate the relative slenderness that is used in the Eurocode. And for stainless steel girder, there is no available design models yet. The flange buckling resistance of corrugated web girders in carbon steel, calculated according to Eurocode, often overestimates the buckling capacities, and this is more pronounced for slender flanges in cross-section class 4. So the major weakness of the model is that it doesn't consider important parameters such as flange to web thickness ratio and segregation geometry. So more specifically, it's the enclosing effect that is shown in the picture here.
Yes, so there is an experimental and numerical study conducted by Jaeger et al., published in 2017 on the flange buckling resistance of trapezoidally corrugated web girders in carbon steel. This is the most extensive research done on this subject, where 16 girders were tested in 4-point bending to failure. And this was followed by a large-scale numerical study on girders with different geometries. So in our analysis, the middle corrugated part in the constant moment region was modeled in the finite element software with the appropriate boundary conditions and two end moments, as seen here. So, with the lack of available design models on the flange buckling resistance of trapezoidal corrugated web girders in stainless steel, the objectives of this thesis are to perform a numerical parametric study and investigate the buckling coefficient and the reduction factor related to flange buckling of trapezoidally corrugated web girders in stainless steel. The second objective is to then establish the relevancy of existing models for carbon steel girders applied on stainless steel beams. And lastly, if these models prove to be unsatisfactory, a new model is developed. And regarding our limitations, we should mention that only the stainless steel grade of duplex 1.4162 is treated, and that no physical tests were performed in the study, only finite element analysis in Abacus. And to conclude the validation study, all observed failure modes in physical experiments on carbon steel girders were reflected in the analysis, and even the ultimate capacities corresponded quite well.
So our next chapter is the first half of the parametric study, the linear buckling analysis. So the base of our parameter range has been dimensions used in the bridge girders. So in total, 450 girders were analyzed. So for most of the girders, the first buckling mode was the unrestricted rotation of the compression flange, as seen in this 3 example here. So unrestricted rotation was noticed. So to conclude the linear buckling analysis, here is the comparison of the Eurocode model with the obtained results. On the vertical axis is the ratio of the buckling coefficient according to Eurocode divided by the buckling coefficient from the analysis. And the horizontal axis represents the slenderness of the flange. So it's obvious that the Eurocode model leads to a large scatter. And the model of the Jaeger et al. Shown an improvement in scatter and safe side results, but still considerable scatter. Taking into account more relevant parameters, the developed model of this thesis shows a much lower scatter, and the results have an average overestimation of only 3%.
And on to our second half of the parametric studies, the nonlinear analysis. The initial mechanical and geometric imperfections are considered through an equivalent geometric imperfection, where the first IN mode is amplified by a factor depending on the corrugation geometry. The required reduction factors from the finite element analysis were calculated as the ultimate moment capacity divided by the plastic axial capacity of a flange times the lever arm between the flanges. So finally, we summarize the comparisons of the different models with regard to ultimate moment capacities, starting with the Eurocode, using lambda as a function of the buckling coefficient given in the Eurocode itself, and then using lambda as a function of the critical stresses obtained from finite element results. The model of Jaeger et al., proceeding with the German Dust-Richtlinie 015. And lastly, the developed model with an average underestimation of 13.9%. And here are the standard deviations of all models compared to each other, just for reference. To conclude, what we presented was a numerical study to investigate the buckling coefficient and reduction factor for slender flanges in trapezoidal corrugated web girders in duplex 1.4162 stainless steel. And that is due to design models being developed for carbon steel and not stainless steel. Comparing the buckling coefficient from the finite element analysis with the method of the Eurocode showed that the Eurocode is not accurate at all and leads to many overestimations. The model of Jaeger et al. Is better, but is not accurate enough. So in developing a new calculation method for the buckling coefficient, it was shown to be valuable to consider many corrugation parameters, which was taken into consideration. And lastly, comparing the ultimate moment capacities from the finite element analysis with existing design models. Firstly, the Eurocode resulted in overestimations for almost all studied girders, and this was concluded to be the result of the too high slenderness limit suggested of 0.748, where 0.4 would be more reasonable. The model of Jaeger et al. Had some improvement in the lower slenderness range, but was still inaccurate. And lastly, the Dust-Richtlinie was the least accurate model. So, given the results and the gained insight, a new model was developed in this thesis for estimating the ultimate capacity of trapezoidally corrugated web girders in stainless steel. And the buckling curve expression is based on the relative slenderness ratio as a function of the developed kappa sigma approximate expression. And the new slenderness limit is then 0.4 according to this expression, as seen in the illustration here as well.
Yes.
And that was all from our part. Thank you very much for listening. Welcome with questions.
Thank you. Thank you for your presentation. A little bit over time, but we have to be forgiving at the beginning. I would like to invite the jury members if they want to raise a question here. Please, Ulrika, unmute your microphone and raise a question.
Thank you very much for the very nice presentation. I like to start with your very beginning that you said that the corrugation is has mainly the purpose of being against shear buckling. But concerning this transverse bending, of course, the corrugation has also a certain effect. Can you describe from the mechanical point of view what the corrugation has an effect in the transverse direction?
Yes, so a major drawback of having a corrugated web is the reduced axial capacity, actually. So in many calculation models, the actual stiffness of the web is completely left out. It's not considered at all. So it's only the flanges that are considered to be working in bending. Now for the transverse bending caused by the eccentricity of the flat segments or the longitudinal segments of the corrugation, that's not something that was taken into consideration or analyzed explicitly. It was purely finite element analysis that were analyzed, and yeah, the results were structured in a way that a new model could be developed, partly for the buckling coefficient, and then later on for the consequent reduction factor that could be expected.
Okay, thanks. And just a second question. Your focus was the change of the material. So the original investigation was for carbon steel. You did the investigation for stainless steel. Can you express what was the most influence parameter of this material change? Is it the E modulus? Is it the strength? What was the most influential, or how did it influence this material change?
Yes, so as known for most of you, I would presume stainless steel has the characteristic of a stronger nonlinearity compared to carbon steel, and somewhat lower stiffness, Young's modulus. So for carbon steel, it's 210 gigapascal, and stainless steel, it's around 200 gigapascal. But of course, we could see that a much higher strength was obtained when changing to stainless steel, and that's due to the much higher yield limit, of course. We have some diagrams or graphs in our thesis that we could show very quickly just for comparison. So here we're trying to illustrate the strong nonlinearity of the stainless steel as material. And there's no clearly defined yield plateau or yield limit. So it's instead the 0.2% proof strength that's used as yield limit, just for reference. But yeah, to summarize, much higher strength, lower stiffness. It reflected the material model.
Thanks very much.
Thank you so much, guys, for the presentation and for the questions. Now it's time to move on to our second nominee, who comes from the University of Naples, and it's Massimino Gnazzo. So the floor is yours.
Okay. Good morning. Can you hear me?
Yes.
Okay, nice. So, hello everyone. I am Massimino Gnazzo, and I am a graduated civil engineering student in the University of Naples, Federico II. Today, we'll discuss about my master's degree thesis in the design optimization of high-rise buildings equipped with sharing force devices using the PBSD approach. The thesis work was developed during an Erasmus internship at the Luis Bozzo engineering company based in Barcelona. The presentation is divided in 3 parts. In the first one, I will introduce the sharing force device. In the second one, I will talk about a case study in which I was involved during the internship, and the last part contains the conclusions. So the sharing force device is a steel metallic dissipator designed by the Luis Bozzo engineering company. And in the last 20 years, the device has been interested by a large experimental campaign in order to improve its hysteretic behavior. The experimental campaign led also to the definition of 4 generations of the device. One main significant feature is, of course, that the dissipative windows of the device are obtained using a milling machine. So in that way, the entire dissipative part of the device is realized without any welding. The sharing force device presents 2 working modes. Initially, it is characterized by shear behavior, and the device dissipates energy through the progressive yielding of the dissipative. And after the buckling, there is an additional source of energy dissipation in a bending way. In a bending way. The main significant feature of the latest SLB generation is the Butterman connection. that is a particular connection to avoid the axial load transfer to the dissipator. Considering the results obtained with the abacus in a finite element model, the numerical force displacement relationship shows a great correspondence with the experimental one, while the von Mises stress distribution confirms that the stress is mainly concentrated in the dissipative windows, as expected for this type of device. The SLB device can be placed in the structure using the diagonal steel braces or decoupled concrete bolts. And this second application is the most widely used today, in case of which the SLB system is placed in reinforced concrete structures. The case study consists in the structural design of a 25-story reinforced concrete building for which the use of SLB system has been proposed as an alternative to the bare frame solution. The structural design has been carried out using the performance-based seismic design approach, following the provisions of the reference codes that are listed here in the slide. The PBSD approach requires the seismic assessment of the structure, considering different earthquake intensities that are the service level earthquake, the design level earthquake, and the maximum considered earthquake. Regarding the seismic hazard assessment, the site response spectra were obtained from a ground response analysis of the soil, and at the maximum considered earthquake, the structure has also been analyzed with the nonlinear time history analysis, considering the time series that are given here in the slide. The proposed SLB solution consists in 4 concrete walls per level that are placed from story 1 to 20. Each wall is equipped with 2 shining ports device belonging to the 4th generation for a total of 160 dissipators. The comparison between the 2 structures, the one with and the one without the shining ports device, highlights that the use of SLB produce an increasing in the stiffness of the structure, at least in the elastic range, as confirmed by the reduction of modal periods, and more important, by the reduction of the interstory drift ratios calculated at the service level earthquake accordingly to a response spectrum analysis. As mentioned before, the assessment of the structure at the maximum considered earthquake has been carried out using the nonlinear time history analysis. And regarding the nonlinear modeling of the structural elements, the Bouwen plasticity model has been adopted for describing the nonlinear behavior of the SLB device, while a lumped plasticity model has been adopted for beams and columns, in this case following the provisions of ASHI 41. Lastly, for the L-shaped columns has been adopted a fiber-inch model, and in this case, the cross-section of each structural elements has been discretized in a finite number of fibers, assigning to each of them the stress-strain relationship of the corresponding material. These are the main significant results obtained by the analysis at the maximum considered earthquake for the structure equipped with the shearing ports devices. The structure meets all the global and local acceptance criteria imposed by the reference codes, and it is important to observe, considering the demand on capacity ratios at the collapse prevention, that the higher values are related to the SLB, while the corresponding ones for beams and columns are quite lower. This means, in other terms, that in this case, the energy dissipation is mainly concentrated in the dissipators, as it is expected for this type of structural design. Lastly, the seismic response of the structure equipped with the shearing box device has been compared with the seismic behavior of the initial bare frame solution, also at the maximum considered earthquake. First of all, also in this case, the use of SLB system leads to a significant reduction in the maximum interstory drift ratios. In this case, of course, comparing this seismic demand with the previous one, it is clear that in this case there is a very strong nonlinear behavior in the two structures. And considering also, again, the demand of capacity ratios for the structure with and without the SLB, it is clear that in the case of which the SLB system is used, the energy dissipation is mainly concentrated in the dissipator, and this partially preserves from damage also the other structural elements. This is also clear, and this is also confirmed taking into account the static cycle of the most stressed plastic hinge for the structure with and without the SLB system. In fact, for the structure with the SLB, it is clear that the energy dissipation, such as also the maximum plastic rotation of the plastic hinge, is significantly smaller to the one of the bed-frame solution. In addition, the use of SLB leads to a reduction and an optimization in the amount of steel reinforcement used in the other structural element, that is around the 48%. And this means, considering also an economic comparison between the two solutions, that there is an economic saving on the total cost of the structure that is around the 12%. Therefore, the use of SLB devices is also economically justified. In conclusion, the advantages given by the use of SLB devices are the reduction of the interstory drift ratios under seismic loads. The energy dissipation is mainly concentrated in the dissipators, and this partially preserves the other structural elements from damage. And there could be also an optimization in the amount of steel reinforcement in case of reinforced concrete structures. In addition, the SLB is also a cheap metallic dissipator if compared to other type of device. So its use is generally competitive also from an economical point of view. And lastly, regarding the disadvantages given by the use of this system, of course, the assessment of the structure requires more complex analysis, such as the nonlinear time history ones used in these cases, and the use of SLB and their supports may be limited by architectural design choices. Thanks for your kind attention.
Thank you very much for your excellent presentation. I would like to ask a jury member to ask a question. Andreas, are you ready?
I was clapping, but I also want to ask a question. So congratulations for this very nice presentation on this topic. You showed a lot of concrete for a steel award. So congratulations on your bravery to do that. But you did show that steel is the key element to make the structure safe, right? I maybe a question about your last slide in a sense, because I didn't quite understand what is so special, particularly about this shear link, right? There are many types of shear links. There's a Berkeley one, there are more traditional ones. What's the big advantage of this system?
Maybe I can take one slide that can clarify the issue. Okay. Well, of course, the two main significant features, in my opinion, for this type of dissipator, one is related to the fact that the dissipative windows are obtained with a milling machine. So the initial steel element is reduced in some part and in some way in order to obtain these dissipative windows. So in this case, the stiffeners are not welded to the steel element. And also the latest SLB generation presents a bottleneck connection that is a particular connection to avoid the axial load transfer to the dissipator, because it has this toothed shape in order to avoid the transfer of the axial load to the dissipator under the gravity loads and also under the seismic loads.
But would you say I understand the milling, so you have no weld,
Yeah.
Is there
in the dissipative, just in the dissipative part, because of course then the plate of connection are welded.
but would you expect otherwise a weak spot in the weld? Is that your concern, or is it an economic question?
No, of course I would expect that, as we know, sometimes the welding is a critical issue for the steel structures in general, and can sometimes change the mechanical properties of the steel locally. So, of course, if it is possible, in this case, I think this can be an advantage if there is no welding. But of course, I don't think that is more economical than the welding solution from this point of view.
Yeah. And if I may, another question directly for me. I noticed in your thesis that you're using a lot of, you're mostly referring to American literature.
Yes.
Is there, it's a bit a loaded question. Is the Eurocode not good enough for seismic design, or
no? The reason for this? The reason was that the case study of this building was located in Mexico. So this is the reason why I used the American building codes in general.
But the Eurocode would have
would be maybe, of course, another great solution to study this problem. But in this case, I needed to follow another type of provisions from other reference codes.
Both very much for this nice discussion. I would like now to turn the attention to the screen because I have our second keynote speaker, the full professor in structural engineering and head of the Department of Structures for Engineering from the University of Naples, Federico II, Professor Raffaele Lador. The virtual spotlight is yours.
Yes. Good morning. Good morning. Are you able to see my screen? Okay. Good morning to everybody. It's really a great pleasure for me to have this to make this presentation dealing with the resilience of steel structure in the seismic for the seismic application. Let me just to move okay. Okay, here you can see the contents of my presentation that basically is composed of three main parts. First of all, an introduction. Then I will try to explain why steel structures are so resilient system for the seismic application. And finally, I would like to show you some recent research project that can confirm this statement. As an introduction, let me, one moment, because there is a problem with my screen. Sorry. Are you able to see? Okay. I would like to start with let me say, an obvious consideration that earthquakes are natural phenomena that have always occurred and unfortunately always will occur. So in this picture, you can see the main significant earthquakes occurred in the last 30 days. So the problem is to try to reduce the huge effect of the earthquakes. And with this regard, I think that we cannot avoid to start to mention the recent experience in Turkey and Syria, where last February we had a very, very strong earthquake, series of earthquakes with a magnitude of higher than 7, and with a tremendous value of the peak ground acceleration and the spectral acceleration, that is the one acting of the building, as you can see, is higher than 1.5 G. So it's a tremendous acceleration. And this can explain the so huge and heavy damage that was occurred in this country. And this is another demonstration that confirm why we need to defend against earthquakes. And a modern way to approach the problem of earthquake is to talk about the seismic risk, because the seismic risk is a combination of three main factors: the hazard, the element at risk, and vulnerability. So we're talking about an urban context in which we cannot reduce the element at risk. Then the strategy for the mitigation of the seismic risk must be based basically on two actions. First one is a reliable evaluation of the seismic hazard. That means to have a good seismic classification of the country. And the second action is the reduction of the seismic vulnerability by means of the good design of the new building and the retrofitting of existing building. Now, the question is, which could be the role played by steel structure in the mitigation of the seismic risk? And we can look to the lesson learned from previous earthquakes. And as you can see, the excellent performance of steel structure was stated still in 1991 by American Iron and Steel Institute after an important earthquakes in USA. Unfortunately, today we have not yet a detailed report on the damage in Turkey and Syria earthquakes, but I would like to share with you two experiences. And the first experience dealing with an important earthquake that occurred in Italy in 2016. Also, in this case, you can see that the magnitude of the earthquake was higher than 6, and with a lot of damage on the building, in masonry building and concrete building. And I can tell you that after the earthquake, a specific study performed by a consortium of Italian university devoted to the assessment of construction damage in the whole area. And as you can see that from this investigation, that only 2% of steel buildings suffered a high damage, and while more than 90% of buildings were with no damage at all or lower damage. The second experience dealing with another aspect that, in my opinion, is very, very important for demonstrating the performance of material in the seismic application. I mean, the use of that material in the reconstruction. Here we are in New Zealand, in between 2010 and 2016, there was a very strong earthquake that destroyed completely the city of Christchurch. We organized in that city a conference in 2018, and during the conference, there was a very interesting presentation coming from our colleague that demonstrated that more than 90% of the total floor area in the reconstruction of Christchurch was supported by steel structure. So this means that the steel was the best option for the reconstruction of Christchurch. And in fact, the city was a sort of open lab where it was possible to see each kind of steel structure. And this was a very, very good news for us. So now I would like to say why steel structures are so resilient for the seismic application. Let me just to remind you that resilience is a general concept. If we apply this concept to earthquake engineering, we can say that a seismic resilient structure must provide a reduced probability of failure, and high energy dissipation, low damage, and must be easily repairable. Steel structure provide all these characteristics. Why? Because all these characteristics are strictly connected to material properties in terms of strength, ductility, low weight, and repairability. Let me just quickly say something. If we talk about strength, I can remind you that steel is the material with higher strength-to-weight ratio. That means good performance, it means lightness of structure. But in the seismic application, even more strength is very important ductility. And if we look to ductility, we can have an excellent ductility at each levels, material levels, member and connection levels, structural system level. This is the reason why, in my opinion, steel is the best solution when you design by using ductility as design strategy. And because in this case, you can have a lot of options. For example, in case of a moment resisting frame, you can locate the plastic deformation at the end of the beam. In case of concentrically braced frames, you can have a good behavior locating the plastic deformation in the bracing. And in the eccentrically braced frames, you can use the good behavior of a link for dissipating the energy. But in addition, you can also use the connection for this plastic deformation. So you have a lot of possibility for well-designed steel structure by use ductility. But this is not only the main aspect, because when you design by using ductility, means that you are accepting the damage. And this means that you must be able and must be ready to repair the structure. And also in this case, the steel solution can be the best one, because I will show you later on some system that can be easily repairable, easily replaced. And this is a very good aspect for the seismic application. Finally, you can also use lightness as a seismic design strategy, because in case of steel structure, you can also have some solution like the lightweight steel framed construction that, thanks to the lightness, can be designed without using ductility, but can be designed in elastic phase, and so without damage. Let me just to show you quickly some research project in which we can confirm this statement. The first project is the Bouwen project that was developed by a consortium of European University. As you can see, during this project, we performed a full-scale experimental test on a dual eccentrically braced frame with removable links. So the idea is to have the plastic deformation in the link, to use the recentering behavior of the multi-resisting frame. And this was a very, very good seismic option. Here I'm showing you some video in which you can see the plastic deformation of the link during the test, according to design concept that I explained before. I have not so much time, so I will go quickly on this movie. And in the next movie, I just would like to show you quickly the phase in which there is the replace of link after the plastic deformation inside. And these two external moment resisting frame provided the recentering properties in order to have the structure in a perfect vertical position after the plastic deformation. This is an example of to have a system with easily repairable. Another example is this project. The name of this project is a Freedom Project, in which, as you can see, there is a different concept. This kind of connection is based on the friction dampers. And as you can see from the movie, we can have a very large rotation capacity without the plastic deformation. So this means the possibility to dissipate the seismic energy without damage, without plastic deformation. Another possibility of steel structure. Another project, here, this is a recent project, and I am the coordinator of this project. The tests have been performed in Staal lab in Paris, and the aim of this study was to study the response of a moment-resisting frame equipped with the different types of demountable fuses. Demountable fuses means a zone in which we are going to have a plastic deformation, but can be replaceable. And I would like to show you the tremendous and as you have seen a tremendous seismic input without important damage. This is a very, very good results. Finally, lightness as design strategy, lightweight steel framed construction. Another research project, European research project, ELISA project, devoted to study energy efficient, lightweight, sustainable, safe steel construction. The solution in order to get this performance by building was to use a lightweight steel construction that was not only good design from a seismic point of view, but also from energy point of view, thermal point of view, fire point of view, and so and so. In Naples, we performed the seismic test in order to check the good performance of this system. Here you can see some phases during the construction. And as you can see, look to the weight of the complete building. It was a very, very low weight. Even if in the picture seems to have a concrete mock-up, in reality, this is a very, very light structure. And thanks to the lightness, we apply to this system a very, very strong real earthquakes. That was the earthquake that occurred in Italy in 2009 with a lot of huge damage. We apply an earthquake 1.5 times these real earthquakes. And once again, you will see that the damage will be very, very low due to this lightness. So, in conclusion, I think that the problem of seismic risk is for sure a crucial issue in all around the world. The lesson learned from the past earthquakes demonstrate that the steel structure can provide an excellent behavior also in the past. The resilience of steel structure is a consequence of the material properties and technological requirements. And also this project that I quickly show you confirm this statement. So in my opinion, the last sentence is, please don't forget to use steel in seismic application. Thank you very much. Milan?
Thank you so much for this insightful presentation. We now move on again to our nominees. The next one comes from Delft University of Technology, Philip Zworzek. The virtual floor is yours.
Okay, thank you for giving me the floor. I'll just share the presentation and let me know if you can see the presentation. And can you hear me? Okay. Thank you for giving me an opportunity to present my work performed for my master thesis topic titled Finite Element Modeling of a Transmission Steel Lattice Tower based on LiDAR point cloud data. In this presentation, I will divide it into 4 separate sections, starting off with a short introduction, giving you some background behind the reasoning and the motivation behind my work. After that, I'll, in methodology, describe the entire modeling procedure performed for this thesis. In the third part, I will focus on the results for both the geometric comparison and finite element analysis results. And finally, I'll draw some conclusions based on the work. So starting off with the introduction. To give you the background, in 2005 in Germany, power grid lattice tower failures occurred due to severe ice and wind loads. This phenomena is a reoccurring event for power grid lattice towers. During that problem, German utilities needed to reassess the structural stability of their lattice tower power grid. And what came out of it is that for a lot of those lattice tower structures, there is outdated or even missing documentation for towers which were erected over 40 years ago. This thesis tried to address this problem by proposing an innovative solution to generate a 3D geometric model using point cloud data, which also is supposed to refine the finite element analysis procedure by using the real data of the structure instead of design documentation. When it comes to the methodology, I'll focus on the modeling process performed for this thesis. The entire approach can be split into 3 sections, starting off with a global segmentation of our tower into smaller segments. After that, in each of those isolated segments, we have to identify each member and cluster it into a separate data cluster. When looking on the member level, we can finally depict the corner point of an L-shaped profile and fit a polyline to each of those members, which will conclude the modeling procedure and allow us to generate the 3D model that can be later utilized in finite element analysis. Now I will present to you the entire process in a short video. We start off by the global segmentation, and each segment is isolated and as depicted in those different colors in the video. After that, in each of those members, we isolate segments, we isolate each members. Finally, for each of those isolated members, we fit the corner points of the L-shaped profile to which a polyline is fitted and allows us to create the 3D model, which we can later on use in our analysis. The proposed method allows for an automatic geometrical model generation without the need of manual processing and predefinition of analyzed tower geometry. The entire process has been scripted, and as an input, it uses the point cloud data, and as the output gives us the 3D CAD model. The positioning of the system line for the structural members are also based on the geometry of the in situ analyzed lattice tower instead of using the geometry based on design documentation. The generated model in this thesis was later used to compare the real data of the model based on the point clouds and the design documentation at 2 stages. The first stage was a geometrical comparison at which the 2 models, the model based on design documentation and model based on the point cloud data, were compared. The blue model depicts the model based on the in situ data. The green and pink models depict the models based on design documentation. As you can see, the bigger the biggest deviations occur especially in the connection region, where the eccentricity of the connection and also the differences caused by the shift of the real position of the members compared to the design documentation occur, which leads to divergence in geometry of the real structure compared to the one based on the design documentation. Those deviations had an impact on the finite element analysis results. Based on the results, the three main points can be outlined. Starting off with the deformation. The response of the point cloud-based model to the applied loading was equivalent to the idealized model. For both models, the same failure mechanism occurred by the failure of the main diagonals in the bracing of the segmented element of the structure which was analyzed. Even though the deformations were very similar, the large divergence in force redistribution caused by different imperfections and eccentricities added to the in situ-based model caused the difference in results when it comes to the force, the internal stresses for the analyzed member. The difference was up to 60% comparing the model based on the in situ data and design documentation. What is more, the initial imperfections introduced to the point cloud-based model led to a significant reduction of members' ultimate resistance, up to 30% reduction for 3 out of 6 analyzed members. To sum up the conclusion, based on the finite element analysis results and showcasing the usefulness of the model based on the real data, final conclusions can be brought. First of all, improved efficiency, which allows for a fully automated model processing, enabling repeatable results and saving time, which would be normally required for manual drafting and processing to achieve such a model. This increased efficiency can result in a reduction of project timelines, costs, and resources required. Second of all, improved safety. By accurately capturing the geometry of the in situ structure and generating precise CAD models, this method can help to identify more precisely the elements of the structure which are to be reinforced or replaced. Also, the increased durability of the structure. By enabling to more accurately measure and assess the structural stability of this using this method, it will allow to extend the lifetime of such a structure and again increase its use case. And thank you for giving me this opportunity to present to you this work. And yeah, I would like to finish my presentation.
Thank you, Philip, very much for your presentation. I would like to give the floor to Professor Feldman. Marcus, please.
Yeah, thank you. Thank you, Philip, for a very clear presentation and give an insight of what is today feasible in so to say electronic monitoring and data acquisition of existing structures. First of all, I have several questions. One is you have mentioned in your thesis that there are different methods how to with which you can obtain these data clouds. One is an aerial and one is a terrestrial thing. Could you please explain the difference of the two?
Yes. So the difference between the two scanners, the terrestrial scanner and the aerial one, comes from the way we mount the laser scan of it. So when we mount a laser scan or on an aerial device like a drone, for example, we will scan our entire structure or an object with a semi-equal distance at all the instances. So our scanner will move around the structure with a very consistent range, and which allows to make sure that the data is very consistent along the height and the length of the entire scan. Whereas when we scan using a terrestrial scanner, the closer we are to the object, the better accuracy and the quality of the point cloud data we acquire. Meaning that for very large structures, capturing the highest parts of those structures will end up with a lower resolution of our point cloud data compared to the lower parts of the structure.
And with regard to imperfections, which today is the system of a preference, considering imperfection.
Yes, so considering the imperfections, the more the technology moves forward, the higher level of accuracy we are able to achieve with such a data. And for now, the precision does not allow to capture, for example, the cross-sectional positioning of those members, because we cannot capture that position of the cross-section much precisely, but we can only capture the longitudinal positioning of those members, which means that the bending imperfection can be included.
And with regard to movements that possibly occur during the measurements, can you take this into account or eliminate these effects like this?
Yes, exactly. So for very high structures, it's very important during the data acquisition to also capture the weather conditions, the wind loads that could be loading our structure. And a good practice is, while creating the model and before analyzing it, we can add and reduce, subtract actually those deformations caused by the wind loads by our analysis, and take that into account.
And a very last question, maybe a more comment. I saw that is a very high transmission tower, more than 100 meters in height.
Yes.
It is. I was amused to see that it is very, very in the neighborhood of the Arcelor steel mill in Bremen, just on the other riverbank. Was it to prevent that it is possibly falling on the steel mill?
Yes, actually, indeed, that was the case, and it was a very special case because this tower was a cornering tower, which was loaded in a very critical cable setup. So yes, it was a pretty important tower.
Okay.
Analyze.
Thank you.
Thank you.
Thank you both so much for this conversation and discussion. We're now going to move on to our fourth nominee that comes from the University of Stuttgart Institute of Structural Design. Laura Katrina Nachebauer, the virtual spotlight is all yours.
Can you hear me? Yeah, now we can hear you.
So, well, thanks for this opportunity. My name is Laura Katrina Nachebauer, and today I would like to present my thesis with the topic reliability of bolted steel connections in Germany. All right. The motivation or question I dealt with was how reliable and safe are bolted connections in Germany, and is there a possibility to design and dimension them more economically? To answer the question, I carried out a statistic evaluation of the design concept of the DIN EN 1993-18 and the draft PREN 1993-18. And also I did a parameter study. In both cases, with a focus on the bearing resistance of a bolted connection. Those both design concepts of the bearing connections are shown here. On the left side, we have the design concept of the DIN EN 1993-18, and on the right side, the design concept of the draft PREN 1993-18. Between these design concepts, there are a few differences, and the main one is that the design concept of the draft PREN 1993-18 is shorter, since there's no longer a distinction between the direction of the load. In addition, the maximum values of the parameters changed, and the design was extended up to steel grade 100. So let us now turn to the statistic evaluation. I used the evaluation procedure according to the DIN 1990 NXE, and this starts with the design concept. And I mean, we already had that, but then the next step was the comparison of the experimental and theoretical test data, which is also shown here graphically. The next is the estimation of the value correction factor B and the coefficients of variation of the errors. And we had to check the compatibility of the design concept and the test data. The fifth step of this procedure was the determination of the coefficients of variation of the basic variables and the determination of the characteristic value Rk and design value Rd of the resistance. The last step is the determination of the safety factor, or rather the corrected safety factor. All in all, at the end, we had to see that gamma m star had to be smaller than gamma m2, which is 1.25 to be safe, because I only deal with the resistance. The base for my statistic evaluation were the following. I had the theoretical database, bearing resistance DIN 1918 and the bearing resistance to the draft PRN 1993. As the experimental databases, I used 7 data sets from the literature, for example, the background document of the EC3 or publication by PMOS. And all in all, I had 386 experimental results. I now want to continue with the results of the evaluation. The data sets I used were divided into 6 groups, and this table of the results of DIN 1993. On the first column, there's the evaluation group, and of these D grades. Then the second column is the respective number of bolts of the test connections, and in the third column, the number of test results. For the different groups, both the determined value correction factor B and the corrected partial safety factor are shown. I mean, I don't want to show you all of my results, but here's an example. You can see the comparison between the experimental resistance and the theoretical resistance of the Staal group S235, and the value correction factor B is very large, which means that theoretical determined values are significantly smaller than the experimental values, and this is seen on the blue crosses. It also can be seen the differences between the design concepts because caused by the different locations of the crosses and this. On the right side now, additionally, the results of the design concept according to the draft period 1992-18. And I don't want to discuss all of these numbers, but want to show you the partial safety factor of all tests and compare them, because the partial safety factor of the draft period is higher than the one from the DIN, and it's also closer to the gamma M2 factor. So we can sum up that the DIN 1993-18 is safe and reliable because it's smaller than the gamma M2, but the bearing resistance is underestimated, and which leads to uneconomic design of connections. And now we can say that the DIN 1993-18 leads to conservative results. To come to the results of the PRN 1993, it's also safe and reliable, and the bearing resistance is well predicted, and which leads to economic design connection. To sum up, that the PRN 1993-18 is safe and in order to evaluate the influence of the connection geometry to the bearing resistance, I conducted a parameter study. For this purpose, this shown connection was used as a basis with a steel grade of S235 and bolts with a diameter M60 and 0.6. For time reasons, I only show the evaluation for the parameter E1, which is the edge distance in the direction of load transfer. At the beginning, I've already shown that the maximum values of the variables in the design concept have changed, and this results in a ratio factor of 1.2. And this ratio value can also be seen in the calculated bearing resistance, and because the results of the PRN 1993 are always 20% larger than those of the DNAN. However, it can also be seen that only by changing the edge distance E1, the bearing resistance of this whole connection can be reduced up to 40% for both designs. In the end, the parameter study has shown that the edge distance E1 has the greatest influence on the bearing resistance. And yeah, to come to my conclusion, both design concepts are safe and reliable. The design concept of the DNAN 1993-18 leads to conservative results. The draft PRN results in more economic connections, and in the draft PRN 1993 only the edge and the whole distance in the direction of the force of an influence on the actual bearing resistance, and the edge and whole distance transfers it to the force have no influence on the actual resistance. Additionally, I can say that the DNAN 1993 may reduce the calculated bearing resistance by including the parameters E2 and P2. And to answer the question from the beginning, the bolted connections in Germany are safe, but with the draft PRN 1993-18, there was a possibility found to make the connections even more economic. So thank you very much for your attention.
Laura, it is time now to introduce another jury member. Leroy, are you ready to ask questions to Laura, please?
Yes, I am. Can you hear me, Laura?
Yes.
Good. Well, thank you very much for the presentation. It's very nice work. I've got a few questions. So my first question is, you mentioned Germany in your title and many times. What aspects of the work are limited to Germany, or is it broader than that?
I mean, the Eurocode is valid for Europe, but I only deal with the German national annex, so I don't know if there are some exceptions, especially for the parameter study. I'm not quite sure if you can use this for all other countries, but I mean the statistic evaluation should be valid for the others.
Yeah, okay. So for the new version of the Eurocode, were you using the rules as they are, or were they modified in some way?
No, I used the rules.
Okay. So probably this should be applicable to.
Yeah, but I as I told, I'm not sure if there are any exceptions in the other countries, so I don't want to say it precisely. Yeah.
Okay, that's fine.
Right.
So you've gathered lots of experimental data, which is great. And I know for bearing, sometimes it's quite hard to define failure in some cases, and some people might use different failure criteria. How did you deal with that?
I mean, I checked at the beginning if this, if my tests even we have this value correction factor V, and you can see if it's in the between 0.85 and I think 1.15, and if this was my main criteria to see if the theoretical and the experimental values are is there great difference or not. And I used this as a main factor to see if this is actually bearing or not, because the main reason or problem with the Eurocode is that, I mean, you don't know if the failure is really bearing resistance or is it the a problem with the net cross section. So that was the main.
Yeah. Okay. And then in some cases, on your when you were showing your B values,
yeah,
for some grades, you know, they were quite high, and for other grades they were quite low.
Yeah.
You know, for example, if you compare 460 and 550, I know the number of tests is relatively small, but there's a dramatic difference.
Yeah.
Do you know why that is?
I mean, I use different data sets, and I know that especially with S46 and S45, there are different tests, so, and not from the same author. So I think that's quite a big problem. But I mean, here we have to also say that the DNA in 1993 is only valid for steel groups up to S460 and not for the greater steel groups.
Okay. And well, sort of observation is good to see that the new code looks to be better than the old code. So yeah. That's a nice outcome.
Yeah.
So that's all of my questions. Thank you.
Thanks.
Thank you all very much. Now we're going to move on into showing you two videos that will showcase the trends in steel construction, information from practice. We have Portland and Severfield that sent us those two videos. You maybe want Frank to say a couple of words for these two companies?
Yeah, maybe we start with the video from Fortman. Fortman, one of our sponsors, and Fortman is a Dutch company, and they developed for many years machines, automatic CNC machines, machinery for the steel industry. So I think they make the steel industry a lot more productive, and so that's an important part of our business.
We're getting consistent output from all of our operators on all of our shifts, where in the past, a lot of times it might vary on the skill of your operator or, you know, or their work ethic.
The operator can focus on processing steel. All these little things the operator doesn't have to know that the machine knows and does for it. And it's made all the difference. Everything is so much faster. We don't have to train as long. And what that meant for us was tripling revenue, probably tripling the steel output.
That's what integration is. It's your machines are doing what they need to do. You can't speed them up. All you can do is slow them down if you're just not paying attention.
very impressive to see what you can do with steel. And of course, what we need is the scientific background of doing this all with steel. Peter, we the same one. We stopped you before you finished your presentation, and we were still waiting for your conclusions. Steel is
yeah. Thank you very much. I think it doesn't make much sense to do it in two parts now. Don't worry about it. Yeah, let's continue.
Yeah.
And of course, I was totally amazed about the videos from Save or Fail. Congratulations, Ellen. So I think it's better to continue now with the program.
Like they're not only professionals in steel, but also in video making. Very nicely done. We can now move on to the last set of nominees. We have Yasser Saleh from the University of Cairo. Please share your screen. We are all ears.
Okay, hello everyone. Thank you for having me. My name is Yasser, and my topic is the assessment of cyclic behavior of frame corner connections fabricated from cold-formed steel. I'll start the presentation with a brief introduction about cold-formed steel, and then moving to the research objectives, the literature review, the experimental work, finite element modeling, parametric study, and finally the conclusions. So as Professor Raffaelli explained minutes ago, lightweight steel structure is an attractive solution right now. It can be used for residential structures, can be used for multi-story office buildings, also building or structures like partitions or domes. This is due to the fact that cold-formed steel has high strength to weight ratio and can give more economic design when compared to hot-rolled steel. The question is, what about the seismic performance or the seismic design of cold-formed steel? So the AISI 400 for the 2020 year edition gives us guidelines for the design of shear walls fabricated from cold-formed steel. However, you can only find one section that discusses the use of moment-resisting frames fabricated from cold-formed steel. So this implied that using cold-formed steel as a moment-resisting frame is an active field of research. Accordingly, this research aims to investigate the performance of cold-formed steel subjected to cyclic loading, whether we use bolts or self-draining screws as fasteners for these connections. So the literature review was divided into three main parts. However, for the sake of the presentation, I'll only mention the screw fasten connections part. So in the literature, you can see that in a paper published in 2017 that investigates the performance of screw fasten connections subjected to cyclic loading. And we can see here the signature curves of the self-draining screws when subjected to cyclic loading. This shape of the hysteresis loops is very common in other researches as well. As you can see here in the 2016 paper and in 2020, the common between these research papers that self-drain screws were used. Finally, to conclude this part, how we came up with the connection or the configuration of the connection tested in the study. We studied the previous work of other researchers, and we came up with the configuration. So the methodology followed in this research was modeling previous work and then modeling our first specimen, then testing the specimen and validating our results of the first specimen, then continuing the testing of the other specimens and validating our work again, and finally the parametric study. So the experimental work, so this is the test configuration that we used. We tested 3 specimens under quasi-static cyclic loading. This is the configuration of the first specimen, where we used self-drilling screws as fasteners for the connection. This is the rendered view. And this is the second specimen, very similar to the first. However, we used an additional top plate that connects the beam top flange with the column outer flange. The third is identical to the first. However, we used bolts instead of self-drilling screws. And AISC cyclic loading protocol was adopted in this work. 40 cycles were applied to the specimens, all the specimens. Of course, we needed component testing to get the material properties of the cold formed steel sections. Also, we tested the self-drilling screws in shear. This is the last cycle that we tested, and this is the hysteresis loops of the test. The failure mode or the deformation observed was in the self-drilling screws where tilting took place, or the tilting of the screws. This is the second specimen. You can also notice here tilting of the screws in addition to minor deformations in the steel sections. This is the third specimen with a different failure mode or different deformed shape, where buckling of the gusset plate followed by buckling of the column section was noticed. Also, the shape of the hysteresis loops differs. You can see it here more better. We can compare the shape of the curves and subjected to cyclic loading. We can see the difference in the behavior of the connections, the different connections. And of course, the bolted connection was superior, but we needed to test the bolts so that we can make a better comparison. This is a comparison between the lab results. So bolted connections were superior in every aspect. However, adding a top plate to the screws provided or reduced the gap between using only self-drilling screws or only using bolts. So the finite element modeling of the screws actually was very challenging, because the phenomena where the screws, when loaded in a certain direction and then reversing the load, so the screw actually tilts, and then when you reverse the load, no load bearing capacity is recorded, and then until the screw returns to its original position, it regains its capacity to carry loads. So this actually was very challenging to model. We proposed our first solution was to use what we called compression-only springs. It was initially very good, gave promising results. However, the only problem, it's a major problem actually, there are convergence errors, especially with large deformations. The second, and it was working and it was adopted in this research, was using the work of previous work by Chuding, which is using or programming user element subroutines, which is basically programming a new element on Abacus using Fortran. The pros is that it works, and the only disadvantage, it's very complicated compared to other techniques. As for the bolts, the modeling, the finite element modeling of the bolts, we used solid elements to model the bolt rather than the famous point-based fasteners. The model verification part. So we compared the deformed shape of each specimen with its Abacus counterpart. And we can see here the stress concentration at the point or at the location of the screws. This is a comparison between the results. You can see the differences reached 18% when loading the specimen upwards. However, only 9% when loading the specimen downwards, in the downwards direction. And the difference in energy dissipation was 8%. This is also the comparison between second specimen and its finite element model. This is the differences between the finite element model and the physical model. And the last specimen, you can see the deformed shape was very similar. And the differences weren't that large between the maximum load recorded, or the moment, or the dissipated energy. So the parametric study, the parameters that we studied was of course, the use of screws only, and the use of screws in addition to the top plate, or the use of bolts. And G3 stands for the gusset plate thickness. This is the naming convention of the models. And R stands for rectangular arrangement. We tested a rectangular arrangement in the column, a circular arrangement, and a diamond arrangement based on work from the literature. The first parametric study focused on the use of self-draining screws only. So SG3, G4R provided the highest performance, or the best performance. However, only slight differences affect the moment capacity or energy dissipation, slight differences between changing the gusset plate thickness. The second parametric study focused on the use of screws in addition to a top plate. Also, the one with the highest gusset plate thickness was dominant. The third study was focused on the bolted connections, and G4R, or the gusset plate thickness of 4 millimeters, wasn't superior in all cases. There were cases, especially when loading the specimen upwards, where the gusset plate thickness of 3 millimeters were better. Finally, with the conclusions. So from the first parametric study, increasing the gusset plate thickness wasn't very efficient, especially because the failure mode was tilting of the screws. So it's changing the gusset plate thickness wasn't very effective. The screws were more critical. And this is actually for all types of models that we modeled, which is that circular and diamond arrangement provided no advantage in terms of strength or energy dissipation. From the second parametric study, a similar conclusion can be drawn. While changing the gusset plate thickness affected the capacity by 16% and dissipated energy by 13%. However, the additional top plate managed to increase the resistance of the connection significantly. This increase reached 41% in the moment capacity and 28% in the dissipated energy. The third and last parametric study, conclusions from it is that the gusset plate thickness only increased the connection by 9%, the capacity by 9% in strength, while 50% increase of the 4 millimeters gusset plate thickness over the 2 millimeters. A very important aspect I included in the study, which is the damping coefficient, where you can see that it's another measure of the energy dissipation, where you can see that bolted connection can perform very well in dissipating energy compared, of course, to the self-drain screws. This increase was 3.5 times. Finally, you can find the testing videos from the paper we published a couple of months ago from this work. Thank you.
Your presentation. Now it's time for questions from the jury. Alan is the jury member. Can you please raise your question, Alan?
Thank you, Milan. Thank you very much, Yasser, for the very good and detailed presentation. You might be lucky with my questions or not, because I'm not an engineer, but we do use in our business both hot rolled steel and cold rolled steel. And I'm interested, first of all, if you have taken your conclusions a step further as to what the implications might be for the practical use of cold rolled steel from the results of your research.
I'm sorry, sir, I didn't get the question. The use of hot rolled steel compared to cold rolled steel?
No, so in our business, we use hot rolled and cold rolled steel. And I'm interested in your conclusions if you have taking the conclusions an extra stage to work through the benefits or the results for the practical use in the construction of cold rolled light steel buildings?
Yeah, so the idea is to, if it's possible to implement or to depend on moment resisting frames in resisting the lateral loads. So in lightweight steel structures, it's very common to use the shear walls setup while using the cold form steel, and it's not very common to use the moment resisting frames. So the idea was to investigate the possibility of using moment resisting frames, and this starts with investigating the connection and the behavior of the connection subjected to moments.
Okay, thank you. And you, I think from your thesis, you used grade S350 steel for the full-scale experimental tests.
Yeah.
Would there be any difference or advantage if you used S450? Do you know?
Any benefits?
Or differences? Do you think?
Well, most of the failures or the deformation was in the connection itself, rather than the cold formed section. So maybe changing the grade, maybe this will change. I'm not sure. Actually, the cold formed steel section, the sections themselves were had higher moment capacity. I mean that the failure occurred in the connections, most of the cases, except for the bolted one, the gusset plate that we observed the failure. So reducing in case of using self-drilling screws, reducing the grade of the steel, I don't think it will affect that much. It won't affect the behavior of the connection that much, since screws failed in tilting. But in the bolted connections won't, maybe that will affect the performance of the connection.
Yeah, okay, yeah, thank you. And final question. I was curious that I think you used Fortran in the programming language rather than Python, which is what the Abacus was using. Was there any reason for that? Yes, or in your choice of the programming language for the subroutines?
Yeah, Python cannot be used for subroutines in Abacus. It can only be used for automating things that already exist in Abacus. Fortran is the only solution if someone wants to like program a new, as in our case, a new element that does not exist in Abacus.
Okay.
Python cannot do this job on Abacus.
Very good. Understood. Thank you for that. No more questions from me, Milan. I don't know if anybody else wants to ask some questions.
Thank you very much.
Thank you so much. I can verify the facts about Fortran and Python. Now we move on to the last nominee that we have for today. Zexi Zhao from Imperial College London. I'm from London. The virtual spotlight is on yours.
Hello everyone. I hope you can see my screen. Is that working? So hello everyone, this is Zexi Zhao, a graduate student from Imperial College of London. The topic of my project is design of steel trusses by GMNA with CSM strain limit. And my supervisors are Professor Leroy Gardner, Dr. Fiona Walpole, and Mr. Huan Chen. So first thing first, normally when we talk about steel truss design, we could go with a traditional Eurocode 3 design approach and followed with Eurocode 3 member checks, or we could carry out design by advanced analysis and followed with cross-section check. But no matter which method we use, the cross-section classification is required. And I mean, we have been using the cross-section classification for decades, and it was designed specifically for the ease of hand calculation. So is there any drawbacks about the cross-section classification? I'd say it does not consider the effects of string hardening, and it does not take into account the actual deformation demands of a structure during its series. And additionally, the classification system itself is based on discrete classes, so it may not fully capture the spread of plasticity. So these drawbacks lead us to a question: is there an alternative method which could replace the cross-section classification? And it brings us to the topic of my research. And the idea is to use string limits. So what is string limit actually? The string limits are taken from the continuous stress method. And as a deformation-based design approach, the continuous stress method features a base curve that defines the level of strain of a cross-section that can endure period of failure. And the CSM strain limit is represented as a function of the local standards of the full cross-section. So for hot rolled steel, we can calculate the CSM strain limit using these two formulas. And now for steel truss design, we can carry out a beam finite element with GMNA analysis, and the analysis itself can capture the beneficial effects of strain hardening, force and moment redistribution, moment gradient effects on member instability. But the extent of these beneficial effects are much more dependent on the failure point. And the model itself can predict member buckling, frame buckling, and material yielding. But at this point, as we are not able to predict anything about local buckling, so we cannot say the predicted result is safe or not. So it's time to introduce our strain limit. The strain limit itself can capture the local buckling to fill the gap of the original beam finite model. And additionally, it takes into account the moment gradient effects on member instability and also include the influence of shear. So now for example beam finite model with GMN analysis, we have the load to displacement curve. So we have totally two cases. The first case is when the CSM strain limit reached before the peak load, the ultimate capacity can be taken at the failure point. Or we could have the CSM strain limit reached after the peak load. And for this case, the ultimate capacity should be taken as the peak load. So this is an overview of the proposed design method. But the primary purpose of my study is to investigate the applicability and accuracy of the proposed design method using CSM strain limit. So we need to create a benchmark shell finite model, and it serves as a reference for comparison purpose. So for the benchmark shell finite model, as we want to make sure this is a representative benchmark, so everything required to be modeled directly. So for the member bolt imperfection, I use the reference value of R/1000 for both in plane and out of plane, and the local plate imperfection suggested by your code 3 part 5, and also the quad linear material model is adopted here to capture the material nonlinearity. And the ECCS radial stress pattern is incorporated into our model as well. So now, combining everything I mentioned previously with global imperfection, the shell finite model looks like this. But please note the amplitude for the imperfection has been scaled to a very large number, just for illustration purpose. And as we want to investigate a wide range of different trusses, so probably in different geometry, different type of truss systems, or probably different cross sections. So everything is pre-processed in MATLAB programming just to streamline the modeling process. So apart from the proposed design method, I have also used some other available design method in the literature for comparison. And before I discuss the design method I have used, it is important to note that the pre-Euro Code 3 part 1 has categorized each design method according to the complexity. So MO will stand for the simplest and M4 for the most complex one. And apart from that, we will adopt a notation from Euro Code 3 part 14 for the LA, GNIA, and GMNIA. So totally we have 5 different design methods. So we have design method 1 here, which is basically a linear analysis followed with Euro Code 3 member checks. And for second order elastic analysis, we have design method 3 and design method 2. They both employ the cross-section check to find the ultimate capacity, but just different in the equivalent Bouwen imperfection adopted and the type of the cross-section check. And apart from that, we have design method 4 and design method 5. They both are designed by second order inelastic analysis and employing the same equivalent imperfection for GMNA analysis and employing the collinear material model. But the design method 4 is using nonlinear cross-section check, and design method 5 is our proposed design method, and of course using CSM strain limit. So from design method 2 to design method 5, they all use the beam finite element model for design, but just differ in the equivalent imperfection adopted and the material model. So for axial section trusses, the element I used here is B31 open section element, and the match size is controlled to be smaller than the local buckling half-wave length. So move to the results. For those results I have generated during my MSc period, as I was sort of curious about when the ultimate capacity is more likely to be governed by the CSM strain limit. So I plotted this graph with member slenderness and the cross-sectional slenderness. So it is clearly to see that the CSM strain limit is more likely to be the governing factor when you have a stocky member but slender in cross-section level. And this result is one of the cases I have looked at. The section sizes for this truss is shown in the bottom table, and we can see from the graph and the top table, the proposed design method 5, has the highest ultimate capacity predictions comparing to other truss design method. And on the other hand, it is only 1.6% lower comparing to the benchmark shelf analysis model, which means the proposed design method is still on the safe side. And for all the cases I have looked at so far during my MSc period, the proposed advanced analysis can use better capacity predictions compared to other advanced analysis methods. And the improved capacity prediction can lead to a valuable amount of material saving and hence contributes to enhance the sustainability. And more importantly, the design efficiency can be significantly improved by the reduced the required assumptions and design checks. And it also employing the computational efficient beam finite elements compared to the shelf alignment model. So save extra computational power. And all of these advantages make the design approach by GMNA become a more streamlined approach. And I think this is why it is being included in the upcoming Eurocode 3. So all of the work I have presented was based on my 3 months MSc project. And after I completed my MSc degree, my supervisor, Professor Garner, came to me and convinced me to do a PhD with him. So I moved on with this topic as a PhD student, but actually it was me bothering him. But anyway, I'm currently trying to developing a more reliable benchmark shelf model to cover more and more types of truss systems. And at the same time, running more results to do the reliability analysis and the parametric study to validate the applicability of the proposed advanced analysis method with CSM strain limit. And additionally, my PhD project is sponsored by Robert Group. So I'm currently working closely with them, trying to apply the proposed design method into real-world engineering project. And with all of this work, I hope I can contribute to the advancement of steel truss design and make a positive impact in the industry. So thanks for your time and patience. I hope you liked my terrible accent. Is there any questions?
Okay. Thank you very much, Zach, for your presentation. We have time for questions of another jury member. Luis, are you ready to ask your questions?
Yes. Well, good morning. Good morning, Sergio. And first of all, congratulations. Very clear presentation. And reading your master thesis was also very, very clear, very concise. So it was possible to really, I think, understand what you did. And good luck for your follow-up as a PhD student. I have a couple of questions. And the first one is really stated in your conclusions of your PhD. And you state that the CSM strain limit eliminates member capacity checks. Is this correct, what you're saying?
I assume you're talking about the traditional Eurocode 3 member capacity checks.
Yes, exactly.
Yeah, if you use the CSM strain limit, then you don't need a member capacity check anymore.
Is it really that, or is it, I mean, because you're using equivalent to method 4 and you're inputting the imperfections, so it's not the merit of the CSM, it's a merit of the fact that you're modeling explicitly the imperfections and residual stresses. So even in your DM4, you don't do explicit member checks, right?
Yeah,
it's not because of CSM that you're avoiding the member check verifications. It's because you're using a more advanced modeling and nonlinear analysis with the imperfections included, right?
Yes, you are correct. Yeah, we don't need the member checks, but in contrast, we use cross-section check, but it's still based on element level.
Sure. And my second question is, we see, of course, throughout your results that you get a very good match between your methods 4 and 5. I mean, GM-in-IA with nonlinear cross-section and GM-in-IA with CSM. They virtually give very much the same result. I mean, not for this example, but the design example that you present, you have 1673 versus 1664. So, and this is very consistent across your details. So basically, it means that M4 and nonlinear plastic gives a result that is very similar to CSM. Do you think this trend is just a coincidence here, or is it something that you expect that will occur throughout your future reliability study and your expanded parametric study?
Actually, I'm looking forward with the proposed design method. So the results showing here is exactly what we expected.
Okay, so I think I will stop for now. And again, congratulations.
Thank you very much. Thanks for the questions.
Thank you, Luis, very much for asking questions and for keeping in time. So we have now to start with the most interesting part. I think we all have become richer for experience, but some of nominees will become richer in money, also in euros. So I would like to ask jury members to place their votes, and maybe you can.
Yes, for the public voting, so you can either scan the QR code that you see hopefully on your screens, or you can open your browser and just type slido.com, and then you're going to be asked to enter a passcode. So that's 3232300. And make sure that you place your favorite project and vote for that one. You only have one vote, so make it count.
Use it wisely.
Exactly. And I think we have a couple of minutes for that. So
yes.
Take your time, read again the titles.
Yeah, we will be back at 1:15. So it is about a couple of 2-3 minutes. It is important that you press the button send, because if you are not pressing button send, your vote is not registered.
We are back.
Yes, if we are back, now it's the time to say the voting. First, I think I can say what is the votes of the public, and the votes of the public provided. It is 62 votes that we have received. The most votes have been received by Massimino Nazzo, the presenter from Napoli.
Ik kan daar helaas niets over vinden.
31% of votes voted for Massimino. So congratulations, Massimino. I will now
Thank you.
That session. And the jury votes is casted. We have 9 jury members who were available to vote. I did not vote myself. And the first candidate is Philip, who received 33% of votes. And congratulations, Philip. And yes, you won. And the second one is Yasser Saleh. You are the second winner this time. So congratulations for both of you.
Thank you very much.
Thank you so much.
I will stop voting for the jury. Yes, you know that the winner will receive also travel to Eurosteel conference. Do we have a slide from Eurosteel conference?
Nice opportunity for Philip to visit again the Netherlands.
Yes.
For a long time.
Philip, do you want to say any words?
Yeah, thank you for giving me such an opportunity to present my presentation regarding my master thesis in such a wide group of people working within the steel structure industry. It's a great pleasure because I'm still working within the topic, and it's a great way to go back to this more scientific a part of that field, coming from now working for now almost 2 years within the industry as well. So yeah, it's a pleasure, and I will be more than happy to present it again in September. So thank you very much.
Thank you, Philip. I think Marcus is also happy, so he can ask additional questions when you are presenting at the conference.
Definitely.
The Bouwen Staal people will help us in communicating with you and arranging the accommodations and traveling. But we also have the second winner this time. I just want to be sure one more time what we said. The vote of the public, oh sorry, the vote of the jury was here. Just let me see what we have. I think I have Yasser. Yeah.
Yes.
Yeah. Nasser, also 22%. So we have an interesting situation here.
Oh, we have a tie.
Yeah, it is not, they are exactly the same.
Okay. We can.
Yeah, did you, no, I think we have to decide with Bouwen Staal how we can split the money. But I want to congratulate both to the team from Chalmers, Ala and Ziad, and also to Yasser. Do you want to say a couple of words from your side, Yasser?
Thank you very much. It was actually very honored. I'm very honored to be with you and to see these presentations. And thank you very much.
And from Chalmers.
Yes, hi. Yeah, of course, we're very honored to have had the opportunity to even be here and present our thesis. And it was a lot of fun, of course, always presenting our thesis. We've had the opportunity to make it several times the previous year. So yeah, this is +1. And thank you very much for having us. A pleasure.
Thank you very much for preparing your presentation and for making very good work. And congratulations to your supervisors and to your university. At this moment, I want to thank all of you because it was outstanding 6 presentations and outstanding 6 projects. How many of you will continue at the university, and how many of you will go in the industry? That is the question that Peter always asks. So at least for the winners, we heard that Philip is in the industry, What about colleagues or students? They are now students, they are now colleagues from Chalmers and from University of Cairo.
I'm currently a PhD candidate at Cairo University, so I'm completing my work academically.
Thank you, Jan. Chalmers, what is the situation there?
In Gothenburg. Yes. So we're actually both working at WSP. So we've been there for 8 months now, directly after graduating. So we're colleagues still.
Yeah.
Very happy about that. And we're actually at the office right now at the moment.
Oh, you are. So we have from four. Oh, yeah, I forget to ask a colleague from Napoli.
Yes, I currently I'm a PhD student in the University of Naples in steel structures. So I'm continuing with the academic career.
Okay, thank you very much.
And we have also
Thank you.
Laura Katrina Bauer.
I think Laura is working in the industry, but we can hear from you, from her, if she is with us.
Yeah, I'm currently working in the industry. University.
Okay, we have heard that it is quite half and half.
Yes, as always.
Yeah, almost as always. This time we had two brilliant female colleagues who presented their work. Hopefully next time we will have more female colleagues. I'm really pleasantly surprised with the quality of your master's work, and I'm very pleased to hear that some of these accomplishments have been done in 3 months. As if I remember correctly, that was in Imperial College. So it was astonishing what is possible to do by our highly motivated students. I think with these words, I would like to finish with the DOS Award. You see that Eurosteel conference is going to be in September, 12 to 14 September. And I hope that we will meet you there, most of you, at least the PhD students. I hope you have continued your publishing work, and maybe even your work from the master thesis. Related to DOS Award, I think you can see that our submission site is open. You see that on this web page. I hope that all jury members will be meeting here at the 22nd of April in 2024. We will also start at the same time at 11 o'clock, working from Bouwen Staal office. Hopefully, then we will have a Microsoft Teams instead of Zoom to make life easy for Anna Marie. That's all for me. Thank you very much.
Yeah, thank you very much, Milan. Thank you for helping organizing this DOS Award again. I think it's a great opportunity for the students to present their work and spread out the information. I think what we shall do is also we publish this in our magazine, and we send it also to other magazines, so the information will spread. And so yeah, we are very happy with this award. And we hope we can continue this to the future.
Yes. Of course, we have to rely on our supervisors at the university to create good projects. And I'm very thankful to jury members who devoted a lot of work for this DOS Award. And finally, I want to thank keynote speakers, Rafael, Peter, and the sponsors, as you want to be always. Without sponsors, we cannot run this. Especially Bouwen Staal cannot run this. University is doing that in our free time.
Thank you so much for organizing it. I think it's the perfect opportunity for students to build their confidence and expand their network.
Yes.
So it's lovely that every year you spend some time to organize this. It's very valuable for all the students. Thank you so much.
Yes, you are one of the one of the nominees.
In the first DOS award.
Yes.
Back in when was it?
Yeah.
2 years ago.
And you were winner of the Dutch Student Steel Award.
Exactly.
And then, of course, all countries have national competition, so to say, because it is important to promote master thesis projects. And then I'm happy that we could keep going with this international award. Hopefully, see you all the next time at about 1 year, 1 day, less than 355 days. Don't forget to put to spread the information about submission to your younger colleagues, and I hope we can have a successful ceremony next year. Thank you.
Yeah, thank you.
Thank you.
Bye bye.